it in my backpack.
Alex, are you Mr. Stewart's class? Are you Mr. Stewart's class?
Oh, pictures.
I'm waiting for Stewart. Stewart.
I'll be here soon.
Here.
Mr. Taylor's on the way, guys. There we go. Mr. Taylor is leaving you guys a message from the other room. He's not here yet. He's finishing up in his last classroom. He's using my computer today, and apparently he can connect with Reflector from down the hall. So he's probably going to do something obnoxious now. Enjoy. You're all set.
Thanks, please.
That's, oh, where is he?
He's in his classroom.
No, he wasn't. I was just there.
He's somewhere, but he's using his iPad on my computer.
Okay.
Good times.
Can do that in my class. Hey, that's cute.
It worked beautifully.
I was swinging it through
Wait, Mr. Taylor.
What?
You just gave out your cute at some point.
No. Okay, fine.
Okay.
All right, Sienna. Are we muted or not muted? We are not muted.
Probably not muted.
Okay. Good stuff. Thank you, Josh. Oh, could you get the doors for me? Thank you.
Super fancy.
Oh, well, thank you. I'm gonna be Josh Gleason as the drive folder. Let me just change.
Yeah.
I just want to go over some assignment sheet stuff for them. And it is sad. Hi, everybody. How was your break?
It's good. It was breakish.
It was breakish.
It was.
All right. Well, good talk. I'm glad we got that out.
Did you guys have like actual breaks, or did you have to go to school still and just not go to this?
No, we had school.
We had school.
Yeah, I know
won't
you
put
guys
next week.
did. Yeah. You have February and April, right?
Yeah.
Yep.
Wow, this is very slow. Very.
Yes, my computer is older than yours.
I forgot my bag this morning and do not have my computer, so I am working a little handicapped here. Okay, so the big thing I want to do initially is show you the final assignment sheet because it is a precipitous motion towards the completion of the course, especially because since we're doing presentations, that'll take a lot of our class time meetings. So there's not all that much time left to do much by the way of new content. Someday this will load. Someday. That day is not today. We did. Did you tell them about the Science Olympiad tournament?
No.
No?
I went and got food instead.
Oh, I see. Would you like to, while I'm doing this, would you like to tell them about the Science Olympiad?
Oh, I see. Oh, okay. I guess so.
All right, fine. Whatever you want, Kira.
I'm waiting with bated breath.
Oh, we had our state competition on Saturday and we won.
As
What?
We won for the 7th time in a row, and people were not particularly happy about it.
We were particularly happy about it.
Yeah, the director said, and in first place, big surprise here, and the other 200 people in the room laughed, and we sat there silently. It was a little unpleasant, and now this is frozen.
But we're going to Nebraska for nationals.
Nationals is in Nebraska.
Awesome.
None of you. I know some of you said you have Science Olympiad teams. Are any of you on a Science Olympiad team?
Losers.
No? Okay. I thought there might be a chance we might see you in. Can I just want to open a document. I'm sorry, Josh. I don't mean to give you a hard.
You can't ask very much of this thing.
Okay. I'm getting close.
Yeah,
I'm almost to the folder I want to open.
It's going to take forever.
I'm almost there.
I can only answer 2 emails a day on that.
Okay. I found a shortcut. Here it is. Oh my God. I think I got it. Share Google Chrome. All right, this is still a little bit of a work in progress. May take 6 or 7 days to scroll through it. We'll find out eventually. Okay, so, all right, there we are. So today, teaching assignment, I have half of them. I'd love to have the rest of them. That'd be awesome. As I said in my email, if you don't have it written up, or you haven't had the chance to teach somebody because things were on break, or senioritis and the lack of formal class meeting times may have affected things, I would much rather you email me and I can give you an extension and have you do it than have you throw something together to pretend that you taught something. This isn't meant to be a high stress thing, but I really wanted to see how it worked for you, and I've got most of them, but not all of them, as I said. So please contact me if you need an extension. We'll work something out. Okay. But looking forward, in class, I decided, because I was looking at how little time we had, I'm going to do topics in solid state physics. You can see we're going to talk today about band theory, then we'll learn about semiconductors, diodes, and transistors. I put them in italics for now because I haven't actually taught much of this in the course before, but I want to try it out for you guys. I'm going to try to make a couple of decent lectures on how we can use transistors to make logic gates. The whole point of transistors is that it's how computers work, and that is why they are probably the most important invention in history. And they're entirely quantum mechanical, which makes it pretty cool. So I'm going to try and say a little bit about electronics. Then we'll talk about superconductivity. Those of you who looked excited when I talked about doing super mathy stuff, I'm going to make some optional videos on computing transmission reflection probabilities of waves in incident on potential steps and things like that. And then we'll conclude. I'll be teaching you about permanent magnetism, which was my line of work. Then finally, I think going to give my thesis defense to you, and I'm going to try and give you a little bit of prep. So you can see inside here it says talk about spin valves, which is a really cool name for something, which you'll hopefully learn something about. So I did work relating to that, and I'll give you my thesis defense from 2003. getting older. And then you will see down here at the end, as we head towards May 8th, we have goodbyes there. I'm predicting 6 presentations. I think we could have as many as 7. So I really think we're going to need 4 class meetings to deal with spillover and people who run over their time and things like that, because I think they should wind up being around half-hour presentations. So we'll really need those last 2.5 weeks, 3 weeks, just to get our presentations done. I wanted to do more than one, but I think I'll just do one. In here, this is going to be a meeting on the 14th where we'll all log in, say, hey, how you doing? And I'll check in with you about your projects, and I'll just kind of be in office hours to answer questions for you about content in your presentation or about stylistic choices, and it should just kind of be a workshop time. Other than that, though, I think I've decided that as far as assessments for the rest of the course, we're just going to have the presentation. Okay, I'm going to teach you some cool ideas that I think are fun, and I mean, superconductivity involves levitation, all right, like actual levitation. So I think there'll be fun topics for you, and then we'll be marching through our presentation. Now, as far as logistics on the presentation, if we look at the assignment sheet closely, you will see, if I can zoom in, checkpoint 1. So I teach this class to second-term seniors all the time. So what I do is I make this as close to 9th grade as possible. This is not an insult, it's an acknowledgement. What we have are like little, like did you write a term paper for your U.S. history course or something? And you had like note card deadlines and bibliography deadlines and an outline deadline. And so like there'll be a deadline that'll be like, you've made a Google presentation, you've given it a title, and you've shared it with the people involved. And that will be worth points. Actual honest to God points. Okay? And you're all nodding. All right. And then this is the crucial one. If I go down here, checkpoint 2, like a little less than a week later, this is the important piece. You have storyboarded. You know what your topic is. You've looked at it enough that you can say, look, I'm going to need 10 slides, and my first slide is going to be the title. My second slide is going to be a picture of a magnet floating over a superconductor, and this slide will be about why superconductors are cool. My next slide is going to be about conductivity, and I'll need pictures of metals or a picture of a circuit. You know what I'm saying? Like really basic layout of what the flow of your presentation is going to be. If you can get that done, the rest of the dominoes really fall very quickly from there forward. That Friday, you have with your group mates put content in there that may need refinement, but you found that picture of that floating magnet over a superconductor. You've picked the circuit you're going to put in there, et cetera, et cetera, et cetera. Then I might move this to like Thursday. The day before we start giving presentations, I'm already shared on the presentations, but everybody's presentations are pretty much in final form. And if you're going to make any edits, they're going to be minor things like changes in font, or you came up with a better title. You're not going to be doing all of your work any time past then. So that we can kind of really just flow through the last couple of weeks, just giving our presentations and learning about cool stuff from each other. And that means that we will conclude the last 2 weeks without any real homework besides the people who still need to, do their actual presentations. The idea is of this final checkpoint here is to make it fair to everybody, so everybody has completed their work by that time, rather than a few people. So the timeline, you also notice that I have excised S and SU from the left-hand column. There are no Saturdays and Sundays listed. So really this is going to focus on, we're going to focus during the week on working on our presentations. Any questions about the flow of the final few weeks of class?
Like, go back to your thesis thing.
Well, let me zoom back out.
What is magnetoptic?
Here, I'll put a hyphen in there for you. Magneto-optic Kerr effect magnetometry.
That makes more sense.
It's the most exciting thing that you could ever study. I think you're all on pins and needles. Okay. Any other questions?
Are we still doing the meeting with the guy from Metaphysics?
Yeah, I got to get back a hold of him. I'm going to try and put him in here, and I'm perfectly happy because these are all just kind of for fun ideas. I'm perfectly happy to supplant one of my talks with him. All right. So yes, I will get that in here somewhere. He was very interested, and then the dates that we gave him, he wound up with conflicts and was traveling. But we'll try again. Any other questions? Does producing a good 30-minute presentation on a topic in contemporary physics spanning from, let me see here, next Tuesday, April 7th, due completed April 23rd, sound reasonable to you? Is that okay?
Yeah.
Okay. Does any of this stuff, looking at those dates on the side, have like significant conflicts with, like, I don't know, exams for you, or, well, I guess it wouldn't, right? Because we're all the way back in April, but I know you guys have somewhat different schedules than we do. But are there any kind of weird conflicts, big trips for your school, or anything that you think would play a role towards the end of April into early May?
Did you share this with us? This with us yet?
It's not in there yet. I'm scared to hit this button because of the way the.
Because
Okay.
I have lacrosse games eventually, but I don't know exactly when they are.
Okay. This is behaving. I'll put it in there now. It still needs some updating. I need to put a few more things in it, but I'll move it in there. Right. Now.
On your
Okay, there it is.
on your Tuesday, May 5th, APs begin that Monday.
Correct. And so I'm hopeful that we would be done with everything. If you have an AP on that Monday, I forget what is those days. We'll take a look. If you have an AP on that Monday, maybe what we can do is, make sure that you get one of the first couple of days so that they're separated from one another. And people who don't, because it's probably, well, hold on a second. Let's just look it up here. AP exams.
Monday is chemistry, environmental science, and psychology. Tuesday is both calculus and then Chinese language and culture.
Yeah.
It's talk in the morning.
If you have a conflict for that Tuesday, if you're taking one of those exams, we can try to make sure that you're earlier in the week. Or I could potentially shift back if it's a real problem for you. So I would say for now, email me if you think you're going to have an issue with your AP exams during that time. Okay, because I know there's several students in the group who have already taken their BC Calculus exam and wouldn't be taking it on that Tuesday. So we might be able to work that out. Anything else? No? Cool.
Oh wait, actually, I do have one thing for me, but it's small.
Okay.
On the 5th, I have an away lacrosse game, so I could probably call in, but I couldn't present on that day.
Okay. All right.
But I
Well,
could
when
call
we pick groups and all of that, I'll create some way in the time issue in the final survey for you to put conflicts into it. How about we do that? I'll put a question about AP exams and a question about other kind of trip and game conflicts during those days. And if needed, I guess I can kill the office hour session and pull everything back by a day, and work something else out. All right. Okay. So, you guys remember any physics? What's that?
F equals MA.
No, that's a good one. We did talk about that shortly before break, actually, right?
We did, actually.
Yeah. What else do you remember? What were we talking about towards the end of our time together?
Schrodinger's equation.
Okay. All right. And what were we doing with Schrodinger's equation?
Letting it really fast.
Yeah. Particle in a box and particle in a finite box.
Okay, we solved we solved the particle in a box problem, right? And we got like solutions like this inside a finite potential well. And the crucial piece here right now is that it's finite. And as opposed to the infinite potential well, what is particularly weird and different about a finite potential well, as my sketch sort of suggests?
Quantization.
It's in the wall.
It's okay. Quantization was in both kinds of wells, but that it's in the wall, that it's leaking into the wall, is different. Now, we talked briefly about the idea of putting two wells right next to one another. Anybody remember anything about that?
Something to do with covalent bonds?
We did. We talked about covalent and ionic bonding by bringing wells next to one another. Absolutely. It was about the allowed states.
Not very much.
Didn't it like
Yeah, go ahead,
connect
David.
through the wall? Sorry.
Oh, yeah. That the wave function could potentially pass through the wall, and that there was one option that looked like that,
The other one was out of phase, or in phase.
and then the other one, it could have been like that. And what did I say about that? Sorry, I'm trying to find a simulation that I had up on my other computer, but not on. Look at those two waves and think about their frequencies. Band structure. There it is. Hey Josh, how does your computer get along with Java?
Questionable.
Okay. Okay, here's me praying. Come on. Oh, settings. Right, I have to adjust your securities. Where's your dock? There it is. It's not even that. Ugh. Oh, come on. No, you. Oh, God. Settings. So look at the two functions. Look at their frequency.
They're gone.
Oh boy, this is not good. There it is. Look at their frequency. Come on, why? What are you doing? What are you doing? I'm trying to get your settings up to allow this program to open, and it's being sad.
Well, it's always sad. You just want to get like security settings?
Why does it keep?
Because the upper right-hand corner is set to just show you the desktop.
Oh,
So you just need to get into. It was.
There it
She
is.
was just loading. You had to give it that 10 minutes.
6.5 hours. Yeah, Dallas.
The green one has a lower frequency and therefore lower energy.
Right. So this wave, even though it kind of looks like it's the same, if you just count the bumps per meter, right, you have more for the red than for the green, and so that we get energy splitting, and that one allowed state is split into two particular energy levels. We have two energy levels instead of one. Security, privacy, federal, open anyway. Okay. Oh, so much sadness.
You use my computer,
It's
but
my
I don't
computer
know.
every day. How do you think I feel?
Can you launch the login?
It's 2 emails a day.
Sometimes 1.5.
So one, it loads, battery dies. Trying.
You're just trying to
It's on my phone, my computer.
Yeah, there's this really cool simulation of all this.
Okay. And you just want to do why is it not?
It said that it is missing a Java tool.
Oh.
Damn it. And I'm trying a different version, ChanLP. Let me try this. Okay, and where's your system preferences?
Should I join as participant or?
This might work.
Okay.
Open.
Yeah, you can download it if you want to.
Yeah, it'll take me a while to install Java on your computer.
What's going to happen? Is my computer going to get worse?
I don't know. All right. Well, hold on. I'm sorry. Give me 1 second. Let me try this on Kira's computer real quick. See if we can get it to work. FET band structure. You know if Java's on your computer?
I think so. Pretty sure.
Yeah, I especially like that I'm like blaming Mr. Gleason's computer when I'm the one who forgot my bag at home.
How could you forget the little white backpack?
Make fun of my backpack.
It's so little.
Where's it downloading to?
It downloaded to like that. Look like the little arrow circle thing.
Oh. Okay, I'll try that. The settings thing again. Your system preferences are missing as well.
Who uses Java?
Everybody who is terrible at programming. I'm sorry. I mean, we can live without the simulation, but it is neat.
What's the website?
It's not a. It's FET band. It's just search for FET band structure, but I don't think.
FET, like an FET.
Oracle should just die.
I'm sorry.
Circles.
Where's
Wish we
your
had spinning
security?
chairs.
FET.Colorado EDU.
Yeah, and it's called band structure. We need the meeting ID. 653 79.
Got it, Ben. I'll share this screen if you want.
Okay. You got it? Can you do it?
I just have to get in Bluetooth.
I'll have to come over there to use it, right?
I've got a wireless keyboard but no wireless mouse. So
Yeah, I'll just come over there. I'll just go over there.
What's the meeting ID here?
653 797 996. Also, Taylor.
You guys stop presenting so I can share this.
Okay. Stop sharing. Okay. Yep.
Bigger, it's not going to side. Oh, here we go. It's over here.
Okay. So this is a set of square wells. I'm going to make it a little taller. And if we look inside here, here's the original energy level. Oh, yeah. Here's the original energy level down there. And if we zoom in, it's been split into two states. And here are the, let me switch it to wave function. Here are the two states, with the real and imaginary part, spinning with time. There's the probability amplitude, where the particle is located. There's two different phases for the wave that give it two different energies. If I jump up to the next energy level, you can see that my original solution for the first energy level has been split into two different versions. This one and this one. And you can see that the functional forms are a little bit more complicated as we get higher. If I go particularly higher, you can see it starts to get really nasty. And if I make the number of wells larger, that something else interesting happens. So if I move up to, I'll go back down to one of these things here. I'll go up to 3 wells. Now at 3 wells, we get 3 different solutions. That one, and that one. 3 different solutions. Maybe I'll put it on.
So wait, like the yellow is the solution, or the?
No, what the yellow is the magnitude of the probability distribution. That's psi squared, essentially. And what orange is the real part of the wave function as it's spinning. If I include the imaginary part as well, you see that it's sort of rotating in time. But these are the different wave functions that are allowed. And when I have 3 wells, it's split into 3 possible solutions. And each energy level is split into 3 possible solutions. If I start adding even more wells, let's go up to 10. We notice that there are, that's some good stuff. There are many, many more solutions allowed. Different combinations of the same solutions for the waves that work together as they leak through the boundaries. So that as I add successively more and more and more wells, you notice, what do you notice? Look at the green lines. Those are the allowed energy levels. What do you notice about, if I take it back down to 1, bring it down to 1, there's our normal quantized energy levels. As I add lots of wells, what happens to the allowed energies? There's 2 things to note about it.
It goes up.
What goes up?
The allowed states.
The number of allowed states goes up, but what else? What do you notice about the splitting?
It's all really dense on the bottom level.
Yeah, it's extremely dense at the bottom level. The difference in energies isn't very strong. As we head up towards the upper levels, the differences start getting a little bit wider.
Change in energy.
Okay. Yeah. The range of values starts out tight and spreads out more and more and more. But I'm with Coleman that what I'm trying to point out is that it's not like the whole well gets completely filled with states. It's not like they're evenly spaced. As they split in so-called bands that still hover around the original value. But it doesn't just become a mess throughout the well. Now, I can make these more like real atoms. I can make the potential, rather than being a square, just a constant value and then 0, I can actually set this to be a Coulomb potential. I'm going to do it. It makes things hilariously complicated, but I'll do it. So you can see that the effect is at least similar. Darn. And I'll go. Yeah. And.
Oh no.
We get state splitting again. Unfortunately, this one won't let me put the states. I can't move the potential up high enough for you to see within it all that well. But we get state splitting again. We'll go back to the square well to be a little bit easier to think about. All right. Yeah. Hey, Josh.
Sure.
Can I boot the sharing of that, or
Possibly because you're a moderator.
I don't know how I can.
You can also just stop sharing.
Okay. So, on to something like, what's the point? If we have a series of wells made by the atomic cores of atoms, like little positive ions sitting down here, And they go on and on and on, essentially to infinity on either side. That is, we make like an actual chunk of like metal, like an actual piece of material. Like we make this remote control out of atoms. Keep holding this thing up. We would get a huge number of wells, but they would be spread out in three dimensions. But let's just focus on the 1D idea. What would happen to the number of allowed states as I built an actual object you could hold in your hand? What would happen to the number of wells and allowed states?
It would increase.
To what?
Is this gonna be like Moore's law or something? Where it like.
We will talk about something related to Moore's law eventually, but what is it increasing to?
Infinity.
Infinity, like something approximately infinity.
Really big.
If you, when you hold human scale objects in your hand, what's a good measure of like a good approximate measure of the number of atoms in a thing that you actually interact with?
A whole bunch.
A lot.
Avogadro.
So many.
Moles. Moles of these things. So that if we like, here's our original n equals 1 allowed energy state. This state splits into multiples of Avogadro's number worth of states. But the key piece that I was trying to show you with the simulation is that maybe you would buy from me that it just becomes really, really dense with states. It's not like the entire set of wells completely fills with states. What we wind up with are these nearly continuous bands of near infinite, essentially Avogadro's number of states. But they're still kind of confined to a band rather than smeared out everywhere. Is that okay? All right. Now, these are allowed states. If you had an actual piece of metal sitting in your hand, and we hadn't put any electrons on it yet, Dallas laughed. It's a horrifying thing. Like you've got like 6 grams of solidified plasma. You're in a bad place right now. Okay, we just have this like perfect lattice of perfectly positive ions. Somehow we managed to hold them together in a lattice work, and then we get like a bucket, and we fill that full of electrons, and we dump the electrons into it.
That just. Science.
Okay. So we zoom in. I mean, conceptually, right? Conceptually, we have all of these empty states. We have this enormous number of empty states there, and maybe we have another band up here. It's a huge number of states, but and I do mean like that these wells continue on in either direction. We have many, many more of them. Sure, there's a huge number of allowed states, but how many electrons will there be?
More?
There can't be more than in the end the total allowed states, but I guess I haven't told you what happens at the very, very, very top. I guess I'm looking for if there's 1 mole of, let's say, let me do this, 1 mole of, I don't know, sodium atoms inside here. How many electrons is this chunk of solid going to take?
Avogadro's number?
More than Avogadro's number, because if it were hydrogen, you'd be right.
Times the number of electrons.
Oh, times. Yeah.
So what is sodium? Sodium 3? Lithium. Lithium is 3. What is it? 9? Something like that. Atomic number of sodium 8.
Right? Should it? I think so. I don't know.
Yeah. So we would
It's 11.
we would have 11.
Yeah.
From the
Okay,
Google.
cool.
Never mind.
From the Google. We have 11 times Avogadro's number pouring into there. Now, we have Avogadro's number of states in this one band because we have Avogadro's number of wells that have split it Avogadro's number of times. So we're going to fill up more than one band as we go. Okay? But where do those bands exactly lie? I'm not going to go all the way back to getting the simulation going. With the actual Coulomb's law potential involved, our bands actually kind of look like this. We'll get a band down here at kind of the lowest state, band, say, here, and then what actually winds up happening is the next set of allowed states is up here out of the atoms in freedom. When we start filling in the atom, we fill in all of these states, filling all of these states, and then, well, out here we have to add electrons into the continuum of states that exist when you're not bound to anything at all. We have essentially free particles at that point out there. And we get more and more and more of them up there. But these electrons aren't attached to the ion cores. These electrons floating around here have nothing holding them in place. So these electrons that are sitting here in this uppermost band above the well, what happens if we take our piece of material and hook it up to a source of electric field?
I'll grab it. Oh no. Pull some of it.
We have inside here this potential well with a whole bunch of electrons confined in the core states, some more electrons here, and then we have these electrons up here that are free. What do those electrons do?
Flow.
They flow. What are these electrons called?
Electricity.
Yep. Other names for them in chemistry class.
Sea of electrons.
This is the sea. Those electrons that are up there in that uppermost band are the electron sea. They are electricity. They are conduction electrons. Now, if we look at the periodic table, I'll wait for this to come up. Periodic table of cars. That's pretty wonderful. What do you know about the periodic table and conductors?
You want it to be in that metallic area in the middle.
Okay. So,
They have
and
the
what's this weird
electrons.
brown, what's this?
Semiconductor?
You have this weird arbitrary line where you have semiconductors, and it probably always felt a little weird that it was so conveniently located. And what do you have over here in this upper corner?
Non-metals or non-conducting.
Non-conductors. So what happens when you go from left to right on the periodic table? So let's go here. Let's start with potassium. We head to the right. What's happening to the atoms as we head to the right?
More electronegative?
They are getting more electronegative, but a little less chemistry class. More just fundamentally look at the numbers. What number is changing as we move from left to right?
Atomic number.
They're getting
And what
larger.
is the atomic number?
Number of protons.
Protons in the
Okay.
nucleus.
How positively charged the nucleus is, right? So here is my potassium atom, or my potassium solid, with a band here, and I have told you that happens that electrons have to fill up this conduction band hovering outside. As I move to the right on the periodic table, the positive charge that was down here gets stronger and stronger and stronger. What happens to the potential function? What happens? Think general relativity and gravity kind of thing. What happens as this ion core gets bigger and more positive? What happens to the well?
The well gets deeper.
Gets deeper.
The well gets deeper. So eventually, what do you think happens to the bands?
It's so deep that they can't escape.
More of them?
Yeah, Coleman's. You're right. Both of you are right. I think Eni said more of them. There'd be more bands confined within. Let me make these a little closer together so we can do that. There'd be more bands within it. And if we just got to the right of the metalloids on the periodic table, what would happen is the next band up would be large enough that we would fill up the atom and make it electrically neutral before we got outside of the well. So we'd have this conduction band up here that is empty of electrons. So this larger ion core pulls the bands deeper inside, and then eventually, as the well gets deeper and deeper and deeper, as we move farther and farther and farther to the right of the periodic table, we pull the valence, the highest energy electrons, inside the well. Now, if they're in the well, what's the deal? If they're trapped inside the well,
They're not really going anywhere.
they can't move. They're not free to move anymore. So we have to apply a really strong electric field. We can apply a strong electric field to get these things to hop up to higher energy levels. But this difference is so large that by the time you do that, you actually wind up ionizing the solid and it catches on fire. So this is an insulator.
Nice.
It's really, really hard to get the electrons off of the ion cores and get them to flow. Things to the left on the periodic table are metals. To fill up the bands, you have electrons that aren't confined to the ion cores at all. Looking at these two diagrams, this one being an atom where there are electrons up in the conduction band, and an insulator being one where there's this huge gap between the valence band and the empty conduction band. What is a semimetal?
Semiconductor?
What would it be? Like looking at these two diagrams, why is there that threshold?
The highest band is just barely in the well.
Yeah. That energy, what's called the energy band gap, is small. It is technically an insulator. We have bands here, here, and let's say that's it. And, I'll make that one a little bit larger. Here's the conduction band up here. This is filled with electrons. This is pretty much filled with electrons. We haven't gotten deep enough to pull this band far enough down so that it really doesn't take all that much energy to pop one of the electrons up into the conduction band and have it move through the solid. So it's an okay conductor, but not a great one. Some other interesting things about this. If I hook a piece of conductor up, metal, to a battery, and I heat the piece of metal up with a flame and make the temperature go up, what happens to the resistance of the piece of metal?
Goes up.
Why?
More collisions.
Yeah. So the way resistance works in a conductor is you have these atoms, these ion cores hanging out. The electrons that are flowing through it don't often interact with them, but occasionally they do, and they get scattered as they try to travel through the solid. What does temperature mean?
Like jostling more.
Movement of the
things that are positive. I can't remember what they're
Yeah,
called.
so if these things are hot, they're
Protons.
vibrating all over the place. So what happens to the probability of scattering?
Increase.
What happens to the probability of running into, like if you're trying to leave school today, all right, there's a hallway full of 8th graders, and they have just had snack. Okay, we have this here. I don't know, like they have just had a bunch of juice, all right, and they're freaking out in the hallways, and you're trying to get out of the building, and they're just bouncing off the walls. The probability that you run into one of them, you giant seniors, on the way out the door, is larger or smaller now that they're running all over the place?
Larger.
Larger. So the resistance to the flow of seniors to their couches goes up. Right? If you cool it down, the electrons can move through the solid with more ease. They have a lower probability of scattering. So the funny thing is, if I were to put like silicon in here, or germanium, and I were to heat that up with a flame, so that the temperature increases, what happens to the resistance of a semiconductor?
It increases.
It goes down, sir.
Or down.
Why? Go back to this drawing. Dallas?
Is it because you're bumping some of the electrons that were inside the well out of the well?
The band gap, this energy band gap, E gap, is small enough that so-called thermal excitation, increasing the temperature, can take these electrons and physically bump them into the conduction band, and now they're free to conduct throughout the solid. So by heating a semiconductor, you make conduction electrons available to conduct. And there's really no explanation for that without band theory. There's no explanation for a semiconductor conducting better with temperature without the idea that these electrons are trapped within potential wells and can only conduct when they have been given energy and quantum teleported to a state that is not bound anymore. There is a diminishing return. Eventually you start to melt the piece of material and the conduction goes away again. But it is a key fact if you're going to learn anything about solid state physics in the very kind of entry level, to understand that metals resistance increases with temperature because the scattering probability increases, and semiconductors resistance goes down with temperature because you are making available conduction electrons. And without the idea of allowed states and band structure, there is no explanation for semiconductivity and no explanation for the behavior of the periodic table. Moving on from there, how does reflection of light work? I know that sounds like totally off the wall, but how does reflection of light work?
That's a good one.
Light bounces off of something and bounces back.
How? Like, okay, what does light like to bounce off of pretty easily? What is shiny?
Metal shiny.
Metals?
My metal is shiny. Light comes in. There are electrons sitting here. What does this wiggling electric field do to the electron? It excites it. Now we can think of it classically and say that it actually vibrates it, and that the vibration of that electron then re-emits that electromagnetic wave in the other direction. From a quantum mechanical model, what's happening is there are a huge number of allowed states. Kind of go like this. And an electron is sitting here in one particular one of those states. The light comes in, and that electron has a continuum of allowed states available to it. So it can be excited to essentially almost any energy level. It's a very fine gradation between them. So it jumps up to some energy level and then spits that energy back out again. But what's key is that the electrons are able to change energy levels to almost anything. So why is it that light reflects off of metal better than it reflects off of plastic? Why isn't plastic shiny? Usually.
Doesn't have the
It absorbs these absorbs more of the photons without re-emitting them?
Yeah, or it doesn't absorb them. But what kind of a thing is plastic? Remember, we've been talking about conductors. It's an insulator. What's the deal with the allowed states for an insulator?
The gap is too big. The gap is too big to pop it up to the conductive level.
Yeah, it doesn't. You can only cause these electrons to jump across kind of fixed states. You don't have a continuum. You don't have electrons in this area where there's a total continuum of states, so that they can absorb pretty much any color of light. Only things with an electron sea can reflect any color of light easily. And so insulators don't have luster, as your chemistry teacher called it. The entire reason why metal is reflective is because of the electron sea, because of the conduction band, because of the continuum of allowed states that it can have. All of this stuff is interconnected. Why are some plastics red? Or green? Or purple?
That's the only energy jump that those electrons can make. That's the only jump they can make to that gap. That gap level is that color or something.
Yeah, there are allowed states that the electrons can jump to that are allowed by the band structure within the solid, so that their color is fixed to a very particular set of values of energy of light based on what the band structure will let the electrons do. So I guess I'm just trying to say that the periodic table and all these kind of solid state quantities, going back to it real quick. Get this up here. All of these things in here, the crystal lattice spacing, the conductivity, whether or not it's a resistor or a conductor, its color, how shiny it is or isn't, is all connected in the end to the depth of the wells, the size of the ion cores, and the occupation of the bands that the electrons go into. And that there is this one explanation, band theory, that explains the behavior of all of these solids. Why is rust, when you have a piece of iron, when it rusts, why does it cease conducting? What do you think? Rust isn't very conductive.
Doesn't have the C anymore. The oxygen's still.
Why not? What happens to the crystal?
The oxygen is too deep.
Not necessarily too deep, but once you have iron followed by oxygen, your set of wells is different from its original value, and the solutions for the bands have changed so that now all of a sudden the electrons fit within the well, whereas they didn't before when it was just pure iron. And because you changed the shape of the potential wells, you have made the system insulating. You could combine iron with some other kind of element that wouldn't do that. Like if we combine iron with some other metal, the two of them together don't make an insulator in the end. It depends on how the two ion cores change the shape of the band structure. You could make something insulating. You could make something a better conductor. You can do all kinds of crazy things to the behavior of solids by changing what is in them. I guess I will leave that at that. So, what do I need for you to move forward? I just want you to be aware that there are bands of states in solids, and that the differences between metals, semiconductors, and non-conductors is simply where the filled states lie on that spectrum. Do the electrons lie in the conduction band? If so, metal. Are they close to the conduction band but not in it? Semiconductor. Are they way below the conduction band and need a lot of energy to get out? Insulator. And that's the explanation for why they are the way they are. And that's it for today. All right?
All right.
I'll see you guys on Friday.
All right. Bye.
Thank you.
Bye.